I told you about this question in the last class, right? I don't know how many of you looked at it. So let me repeat the question. So here we have a rod is being acted upon by 5 forces at the same location and the same orientation. Okay. So you have the freedom of adjusting the size of the force, but you cannot bring it to 0. Okay, that is the condition. And some of these configuration, you can make the rotational equilibrium. That means you can make the net torque equal to 0. But some of them you cannot, no matter what you do. You have the freedom of shrinking the size of the force, but you cannot make it to 0. So how do we do this question? I will do it. I will take this A and I will analyze this for you. And after that, you should be able to check the others on your own, hopefully. So let's see. The fulcrum, where you want to take the torque, okay, where it is the rotation axis, or where the pivot point is also changing. That is changing in different configuration. But the location of the force, there are 5 forces acting in all of them at the same location and the same orientation. So let's start with each force one at a time. I'm going to label this number 1, number 2, so I can easily refer to them, number 4, number 5. So we have the force number 1 acting at the left end at the fulcrum and so on. So let me start with the torque from force number 1 around that fulcrum. What is the torque from that guy? Torque from this force at this point equal to? How do you define the torque? Torque is equal to, the magnitude will be R F sine theta. So let me take one by one. What is R here? R is defined as from the fulcrum or the pivot point to where the force is applied. Draw a line from the fulcrum to where the force is applied. What do you get? You can see where the fulcrum is. Can you see where the force is applied? Same place. So what is the distance from same place to same place? 0. So the torque is 0 from this guy. So I will put this torque is 0. Okay. Number 2. Now is the R 0 now? No. There is, we have an R. And now I need to get the direction of the torque, whether it is clockwise rotation or counterclockwise rotation above the fulcrum. So imagine you put your finger here, okay, the fulcrum, and think, imagine number 2 is the only force. Okay, forget about the rest of the force. Then which direction will it turn? Clockwise or counterclockwise? Clockwise, right? So they say this is the thing I am holding here. This is the fulcrum, and I'm applying the force like this. So it is turning clockwise. It's very easy to get the direction that way, okay? So you are pulling it down, so it is moving clockwise. So the torque from this guy, number 2, is negative, right? So I want to get the direction of the torque, whether clockwise or counterclockwise, from each one of them. Then I will tell you why I am doing that at the end, okay? Let me do this now. Number 3. Right? Counterclockwise, so positive. Number 4, positive. Number 5, What about number 5? 0. Why is it 0? Is it because R is 0? No. Because R is this and F is this. Angle is 0. R and F are in the same direction. So theta is 0. Sine 0 is 0. You cannot, it's like you're pulling like this. Okay, this is the rod and you're pulling like this. Can you turn it? If you pull it parallel, there is no perpendicular component. It has only parallel component. Parallel component can do nothing to turn it. So the torque from number 5 is 0. We have at least one clockwise torque and at least one counterclockwise torque. In that case, we can bring it to equilibrium. Why? We have the freedom of changing the magnitude as you like, as long as you don't bring it to 0. So I can adjust the plus and minus to be equal. Okay, I can adjust the clockwise torque to be equal to the counterclockwise torque. So I can make the net torque equal to 0. We have to pick the one that cannot be made to 0. That means he is out, A is out. One of them, maybe more than one of them, I don't know exactly how many we have here, we cannot bring it to 0 torque at all. Because we will not have either no clockwise torque is present or no counterclockwise torque is present. If you have at least one positive and one negative, we are done. We can bring it to equilibrium, rotational equilibrium. If we don't have, all of them are either one sign, only positive and no negative at all, then we cannot bring it to equilibrium. So shall we check the others one by one? So A is out. A can be brought to equilibrium. What about B? This is B. I'm going to ask you, I'll put number 1, number 2, number 3, number 4, number 5. I'll ask you, you have to tell me quickly. Now fulcrum has moved. Tell me positive, negative or 0, okay? Number 1, positive, negative or 0? Negative? Positive. Do you all see that it is positive? Number 1 is positive. Anyone has a problem? I will explain. Okay. All right. So this is the rod, and where I am putting my these left hand fingers, this is the fulcrum. And the force is like this. Can you see it is going counterclockwise? Okay? Clear? So number 1 is positive. Number 2 is negative. Okay, I want, anyone has an issue, please tell me. This is the fulcrum and the force is applied here, down. So it is going clockwise. So this is, number 2 is negative. Number 3 is positive. Number 4 is positive. Number 5 is 0. We have at least one negative and one positive, right? He is also out. We can bring it to equilibrium, rotational equilibrium. Okay, number C. The fulcrum is here now. Okay, right. Number 1 is positive. Number 2 is 0. You know why it is 0? Yeah. Number 3 is 0. R is 0, right? Number 4 is positive. Number 5 is 0. Do you have any plus and minus? We have only plus and 0. Zeros of no use. Yeah. So, say it again. Number 2. This number 1 is positive. Number 2 is 0. Why is it 0? Number 3 is also 0 because R is 0, right? It is like your fulcrum is here, and no matter how much force you apply at the fulcrum, can you turn it? No way. It's like opening the door. Can you open the door from the hinge? No way, right? Because R is equal to 0. So this guy, all of them either 0 or positive. We don't have any negative. So can you bring it to rotational equilibrium? No, right? Because you have the freedom of adjusting the size of the force, but we don't have any negative force to cancel the positives. So C, is it C? Yeah. C cannot be brought to equilibrium. And the rest of it, yeah, that is not C, that is B, right? This is very confusing. Okay, this is B. And this is C. Okay, sorry about that. Because this is all crowded in. So it's C cannot be brought to equilibrium. D and E, let me go very quickly. Okay, now I hope you can stop me if you don't follow. So this one is positive. This one is positive. This one is negative. You already know there is at least one positive and one negative. So he cannot be chosen. We can bring it to equilibrium. Let's go to the other one. The fulcrum is here. This is 0. This is 0. And this one is negative. And this one is positive. And this one is positive. Okay. So don't look at the direction of the force. Don't think, okay, because the force is up, it is positive. No. Here, look. Up forces are negative. So it all depends on the position of the fulcrum as well. So both of them we have positive and negative. So both are out. Only thing that cannot be brought to equilibrium is C. Now we have a question that we can answer. A figure shows a standard man, 70 kilograms, standing on a flat surface. So one of his foot is shown here, and his heel is touching the ground, and his toes or whatever is touching the ground. So we are looking at this foot, and there is a force where he is touching the ground, that is N1 from the floor on him, and at this point there is another force N2 up and up, and above this, whatever the weight of the person will be on this place. So we are looking at this foot, right? So on this foot we have the N1 at this point, N2, and the weight of the rest of the body through this bone here pressing on him. So we are looking at 3 forces acting on the foot. I hope it is clear to you. So you can model it like, say, this, just something like a rod, and here N1, here N2, and from the rest of the body above him, the weight, not the total weight, because we are looking at only one foot, right? Say the right foot. So the weight will be half of the weight of the man, right? But also you have to subtract the foot. Maybe we can assume the foot has a very little contribution. So the external force will be half of the man's weight, 343 Newton. Is that clear to everyone? Why I took the half? Because we are looking at one side of the body. So the foot is acted upon by 3 forces. Now we make it clean physics problem. So we have something, the foot, and on the foot we have 3 forces acting, N1, N2, and the half of the weight. Okay, so I can apply, because he is in equilibrium, right? He is standing. So the net force is equal to 0. I can apply that because that is the translational equilibrium, which says net force is equal to 0. Net force will be, there are three forces. N1 is positive. From the rest of the body, I call it F external, that is down, so negative, and N2 is also positive. When you substitute value, you get this equation. We don't know what N1 is, we don't know what N2 is, but at least we know N1 plus N2 is equal to the half of the weight, 343 Newton. We don't know what, there are two unknowns in this equation. N1 is unknown, N2 is unknown. Can I solve it? It's like saying, say, x plus y is equal to 5. We have many solutions, right? We don't, infinite number of solutions. So we cannot solve for x or y. At least we need one more equation. Okay. So there is no forces in the x direction. So sigma fx equal to 0 is not going to help us anything. No forces in the x direction. It's 0 equal to 0. So we need something else. That something else is the next equilibrium condition. Net torque is equal to 0, right? Because he is not even spinning, right? He is not only translational equilibrium, he also has rotational equilibrium. So that is here. Net torque equal to 0. That is the rotational equilibrium condition. And now, let me get back to this picture. So I'm going to erase this. It is. I'm going to mark some points. I'm going to call this point A, point B, and point C. Whenever you want to apply the net torque equal to 0 equation, torque, when you want to find the torque, we have to tell about which point, right? So when I say net torque is equal to 0, you need to choose your point. Let me say, call it X now. I'm going to choose the point A, X to be equal to A, or X to be equal to B, or whether you're going to choose X to be equal to C. It is true any point. You can choose any point you want. The condition should be valid. Net torque should be equal to 0, no matter which point you take to apply that equation. So it is up to you. So you choose a point cleverly, wisely. So you come to the answer in very few steps. Okay, you don't just blindly choose a point. You have to choose it cleverly. So which point do you think that I should choose? Yeah, A or C, right? Good. A or C. Why? Yeah, you have the, yeah, why? One unknown. Yeah. You don't want in the equation end up something like this. This guy got two unknowns, then we are kind of stuck. So the wise thing to do is to choose such that you end up with only one unknown. For example, if I choose B, N1 will have a torque, N2 will also have a torque. They are the unknown. F external is anyway we know it, so it is not to our advantage. So either you choose A or C. If you choose A, N1 will not come into the equation because the torque from N1 is 0. So you will have only N2. Then I can solve for N2 very quickly. Then after that, I can go to this guy. Once I know N2, I can find N1. Okay. Or you can choose the point C. In that case, you will find, if I choose C, N2 will not be there. I can find N1, then go back to that equation and find N2. Anyway, so let's follow what he is doing. He is choosing A and see what is happening. If you choose A, the torque from N1 will be 0. Okay. Why it is 0? Because R is 0. Okay. N1 is applied at A, so you need the distance from A to A. So that is 0. What about torque from the external force? So we need the distance from the A to where you want the torque to the point B. It is given as x1, so I will substitute x1. And the force, it is already perpendicular. There is no sine theta. Sine theta is 1. Theta is equal to 90. Sine 90 is 1. And what about the sine? This is very important. Get the magnitude. Then you need to tell me whether it is trying to clockwise or counterclockwise. So you put your finger at A, and the force is like this, so it is trying to rotate it clockwise. Therefore, negative sign. Okay. And then torque from N2. Torque from N2 at the point A, that we need x1 plus x2 will be the R. Multiply by N2, it is perpendicular force, so the whole thing. And the sign will be positive. Because, see, this is the point, it is trying to rotate the foot counterclockwise. So it is positive. So you put positive sign there. Now look at this equation. How many unknowns we have? Only one unknown. N2 is the only unknown. So you write the equation algebraically with the symbols. What you do now, you just go to your calculator. Numbers are there, right? So is it being solved in the slide? No. Okay, so let us do it ourselves. Calculator. Where is my calculator? So let me show how to do it, like solving equation rather than doing the algebra. We will just substitute values. 0, I don't have to write the 0. Okay, there is a subtraction. So, well, just to be complete, I will put 0 minus x1. What is the value of x1? Can somebody help me here because I am covering the day. Okay, 6.2. Do I need to convert it into meters? No need, because I'm going to put everything in centimeter. Every term has a distance, a length thing, so we can keep it all centimeter. So I will write 6.2 multiplied by external force, which is 343. 343. Then you have plus, where am I? Going to the wrong place here. I'm done with this plus. Then I will start the left parenthesis. This is x1 plus x2. So please somebody keep an eye on what I am doing in case I put the wrong value. 6.2 plus 12.3. Close the bracket. N2, what do you do now? Anyone knows? N2 we don't know. We call it x, right? Multiplication sign. How do you get the x? Alpha, right parenthesis, that is x. And then you write equal sign, okay? You have to type the equal sign. So you don't press this equal button. Alpha, yeah. Then you say equal to 0. So we have an equation. You tell the calculator to solve x for us. You don't do any algebra. You don't do any algebra. So how do you do that? You come to this, you ask it to solve it. So press the equal button here, the operation. What did I do wrong? Okay, I did something wrong. Let me check my equation. 0 minus 6.2, okay, multiply by 343 plus 6.2, 12.3, multiply by x equal to 0. I don't see what did I do wrong. That's very strange. 0 minus 6.2 multiplied by 343. Okay, plus 6.2. Yeah, I know what I did wrong. I skipped a step. I don't press the equal button. I have to do shift calc. Yeah, maybe Ramadan. Right. Shift calc. Is this the answer? No. This is the value of x from a previous calculation, which is in the store. Then you have to press the equal button. You should see something like that, x equal to an L minus R, then you know it has solved. So the answer is 114.95. That is the value of N2. Okay. It is good to know this, but if you don't practice at home, you are, even I forgot everything, I forgot the one step. So you should know, you should have practice doing this, then you can go with confidence that, you can skip the algebra part and solve it using the calculator. Right, then I will skip the rest of the thing. Once you know N2, you can use this equation, okay, the sigma phi equal to find the N1. That's easy. Right, shall I move to the next slide? Okay. Right, classes of levers. I don't know, you heard this word levers before. I mentioned that, right? The moment arm and levers. So here, you can model the skull of a person as a lever system. What do you mean by that? Imagine there's a rock on the road. It's very heavy, very heavy. You want to lift it. So one trick to do is put some what do you call that? Some rod or bar like that, and yeah, we put a support here. Okay, put a support here. So you are not strong. You can only apply, say, 10 Newton. Or let's say 10 Newton. You can apply a force of 10 Newton. Say you're weak. But this weight of this is, say, 100 Newton. So, but the force you can apply is only 10 Newton. If you want to lift it, the maximum you can do, let's say only 10 Newton. So say you're weak. But you can still lift it because about this support point, the torque from 100 Newton, maybe this distance is only, say, 1 meter. Okay. So what is the torque from this 100 multiplied by 1 meter? I'll ignore the angle, okay, just to say this 90 degrees, just to show the concept. So it is 100 into 1 is, the torque is only 100. With 10 Newton, can I get the torque of 100 by making this long? So I can give this force at a distance of 10 meters, 1 to 10. I will get the same amount of torque. All I have to do is to increase a little bit, say 12, then I will have a greater clockwise torque, so I can lift the thing. So these are called the levers. Now here we have the support or the fulcrum, also called the fulcrum. In physiology it is fulcrum, okay? The fulcrum means in the middle, and this is called the load. This is called the load, which we are going to try to lift. And this is called the effort. That is where you want to apply the force. So these are the terms: effort, load, fulcrum. So this is when you have the fulcrum in the middle, or the support in the middle, it is called the class 1 lever. Now you have to memorize this, okay? This is something that you have to memorize. What is the class 1 lever? we have three things, right? Effort, load, fulcrum. When the fulcrum or the support is in the middle, it is class 1 lever. Okay. Our skull is a class 1 lever. Let me show it. So this is the skull. So you know the whole skull is supported by, what is it supported by? What is the name? The vertebrae or spine, right? Okay. The skull is kind of actually supported on it. So you know as medical students, right? Okay. So here, this whole vertebrae or the spine and the skull is supported on this. So that is the support. The fulcrum is this. Then the weight of the skull is to the left of the, I'm sorry, no. The weight of the skull is, let's say, to the right of the support. And, okay, this is the skull. The weight of the skull is to the right of the support. And you have the muscle here, which is going to pull this way. So there's the tension from the muscles and the support is in the middle. So for example, you are sitting in my class, listening to my lectures, and if you go to sleep, what happens? The muscle relaxes, right? And you will go like this. Why? The weight is pulling you down, that is clockwise, and the muscle is supposed to pull me in the other direction. If the muscle relaxes, there is no counterclockwise torque, and then you go down. Right. So the lesson here is you should know what we mean by class 1 lever. So there are questions. If you look at the past midterm, I will show this picture and ask you which class does it belong to. So you should remember, because the support is in the middle, it is class 1. So only you look at who is in the middle. Okay, it doesn't matter which side the others are. Okay, maybe load can be on the right side and the effort can be in the left side, or the other way around, doesn't matter. What you should look at is who is in the middle. If the fulcrum is in the middle, it is class 1. This is another one. That is, you are on tiptoe. Okay, so when you do that, the support is here. That means fulcrum is at the end, one of the end. It doesn't matter which end. No, you don't look at the, again, what you should look at is who is in the middle, right? So don't worry about who is in the end or what fulcrum is doing. You just look at who is in the middle. So this is the foot. You have the fulcrum here, and in the middle is the weight, and the effort is, that is the tendon. It's called the Achilles tendon. Achilles tendon is the effort, and the support is in one end, effort is in the other end, and the weight is in the middle, or the load is in the middle. So when the load is in the middle, it is class 2. So that is what you have to memorize. Class 1 is fulcrum in the middle. Class 2 is weight is in the middle. So this is an example in our body. Okay. Number 3, this is class 3. Who is in the middle? Effort is in the middle. So there are going to be 3 of them, right? Yeah, I have a question? Yeah. Okay. We have 3 of them, right? So because there are 3 things: effort, fulcrum, load. When the fulcrum is in the middle, class 1. When the load is in the middle, class 2. And when the effort is in the middle, class 3. The best thing is to memorize the order: fulcrum, load, effort. 1, 2, 3. Done. So class 3 example is the forearm. But who is in the middle? Effort. Okay. Right. That's easy. Next slide shows 3 bent lever arms with the fulcrum indicated by a dot and a single force F acting at the far end of the, nearing the end, right? Anyway, I will not take attendance today. I don't know, because I thought a lot of people absent. So let me continue. Okay, let me finish this lecture. Next slide shows 3 bent lever arms with the fulcrum indicated by a dot and a single force F acting at the far end of the lever arm. Which of the 3 systems is in mechanical equilibrium and does not rotate as a result of the force? Right. So which one will not rotate? A, B, or C? The fulcrum is here, and the force is going through the fulcrum. So that means R is this, right? And F is this. What is the angle between R and F? 180. Sine 180 is 0. So this is in equilibrium. Second one, not 90, not 0, right? Something other than 0. We don't know whether it is 90 or not. So this is the R and this is the F. So some angle, okay, whatever it is. What is the question exactly? What he is asking? Which of the 3 systems is mechanical equilibrium? So A is in equilibrium, B is not in equilibrium, C is also not in equilibrium. There is R value, there's F value, there's a sine theta which is not equal to 0. So only A is in equilibrium. All right, I believe this is the last one. Yeah, yeah, we will solve this question. Yeah. I'm sorry?
None of them are equilibrium.
No, as a single for always unbalanced. No, this is in equilibrium. A is in equilibrium. Is that the answer from the textbook? No. There is not a single force. This is fulcrum. There are other forces at the fulcrum. So that is not correct. I am not sure. I don't think it is the answer from the textbook. I didn't check it myself. I'll check. Because A, this rotational equilibrium is there. Why is there rotational equilibrium? Angle is 180. So cos sine 180 is 0. So we have rotational equilibrium. The other answer, single force, that is not true. There are forces at the junction. There are forces here. You know, this force doesn't matter because those forces will have 0 torque anyway because R is equal to 0. So the net force is equal to 0 going to happen anyway. Just imagine, you apply the force like this. Do you think this is a fulcrum? Okay, it is pinned. This is not going to move anywhere. Also, there are not going to be any rotation. So that is not correct. Okay, I don't know. I will check it in the book. I don't know what went wrong there, but this A is in equilibrium. I'm sorry, I didn't check it myself, but I thought, I know how to do it. Let's see. Anyway, this one, a light board, it's 45. 7 meter in length is supported at his end. I will go a little faster. So he is in equilibrium. So we need to apply net torque is equal to 0 to find the torque tension on this rope, TR. So we have to find TR, and This is given, this is not given. So the best thing is to take the talk about the point A. So TL will not come in the equation. I'm not interested in that. And I only want to find the TR. So let me go to the next slide where it is worked out. So I take about A. So torque from the three forces about the point A equal to 0. Torque from TL is 0, good. Torque from mg will be around A, right? So the 4.5 meters multiplied by the force, weight, and negative sign because it's trying to rotate clockwise, and this one is trying to rotate that way. So positive sign, this is 7 meters, and this is the unknown, and you solve it. Here it is, algebra is being done, so make the TR of the subject, and you solve it, you get the value 536. Okay.